Thank you very much. Good evening, everyone. Oh, don't worry. So something a little bit different tonight. It's the last two lectures you've heard about the landscape around Brampton Bryan and then the close landscape, the park and the castle in particular. So we're breaking with tradition tonight and doing the science of archaeology. I've quaintly called it Trowel and Error. The old jokes are the best. Could have been a career in ruins, couldn't it? Something like that. But Trowel and Error seem more apt. And what I want to do this evening really is to give you a sort of a yomp through what archaeology actually is and how it works. There's a lot of information to take in. There'll be a lot of words up on here. You don't need to read them. I shall speak them for you so you can hear them. So don't worry about that. But basically what I want to try and get across is that digging a hole isn't quite as easy as you might think. There are a lot of things that you have to think about when you're digging a hole, not least why you're digging it in the first place. You know, the problem that we have with digging holes is whether I do it or whether a 20-ton JCB does it, the archaeology is removed forever. It is a finite resource archaeology. It doesn't grow back. Once you've dug it out, it's gone. So when we dig things out now, we try and dig as little as possible to find out as much information as possible. So this evening is really a bit about the science of thinking about archaeology, and then some of the scientific methods and techniques that have been used, certainly since the turn of the century, the last century, up to the present day. And I'm going to try and describe how some of these strange, weird and wonderful things work. Things like LiDAR and carbon-14 dating. And where possible, I shall try and show examples of how it's been used in Herefordshire over the last decade or so. Okay? And there'll be some opportunity for questions at the end. Right, so archaeology, the definition, is the study of human history and prehistory through the excavation of sites and the analysis of artifacts and other physical remains. And there are two main strands: archaeological theory and archaeological science. The theory provides a means of ordering both the process of investigation and provides a framework for the testing of ideas before, during and after an excavation. And the science provides methods and opportunities to investigate and enhance our understanding of archaeological features. And these two strands need to be used in tandem. If you use one and not the other, you won't know what you're asking to get the results from. You need to have an idea, the theory bit, as to what you want, so that the science bit will actually back it up or disprove it. So, a crash course in archaeological theory. The process of archaeology, it really kicked off in about 1860 as far as people's thinking about why they used to find different artifacts of different types in different places. So the antiquarianism, so this really started in 1860, was based on the three-age system. So you had stone, then you had bronze, and then you had iron, and then you had history. So basically they divided up prehistory into three very, very broad bands. And that was easy, but not terribly scientific. And it quickly got usurped by something called cultural historical. So that's after Darwin came the concept of cultural or culture history. The idea groups sites into distinct cultures. So you have things like the Mayan culture, etc. To determine the geographic spread and time span of these cultures. And it basically tries to show how different cultures used the environment and believed different things, but also how ideas spread across areas. And at the same time, really, historical particularism began. You see, I bet you never thought we'd be hearing these words tonight from an archaeologist. This is what you have to learn when you go to university. I don't like it. But Franz Boas argued that cultures were unique entities shaped by a unique sequence of events. As a result, there was no universal standard by which one culture could be compared to another. This line of thought, combined with John Lubbock's concept that Western civilization would overwhelm and eventually destroy primitive cultures, resulted in anthropologists recording mountains of information on primitive peoples before they vanished. And shortly after that, or to sort of coincide with that later, we had national archaeology. So national archaeology was used as cultural historical concepts to instill pride and raise the morale of certain nationalities. 1916 and through certainly the Second World War, Germany was very good at this. Or racial groups, and in many countries it remains the dominant method of archaeology. And then, to outdo that, we have Soviet archaeology, which is adapting some of the concepts of Darwinian natural selection for use outside of the discipline of evolutionary biology, whilst employing the Marxist historic economy theory of dialectal materialism. See? Carefully, yes, if you want. So Soviet archaeologists tried to explain observed changes in the archaeological record in terms of internal social dynamics. Marxist archaeology, if you like. It's complicated, and we make it sort of, in a way, even worse, because we have processual and post-processual archaeology. So in the 1960s, a number of young, primarily American archaeologists, such as Louis Binford, rebelled against the paradigms of cultural history, and they proposed a new archaeology which would be more scientific. And this is my link to science. And anthropological. They came to see culture as a set of behavioural processes and traditions. In time, this view gave rise to the term processual archaeology. Processualists borrowed from the exact sciences the idea of hypothesis testing and scientific method. They believed that an archaeologist should develop one or more hypotheses about a culture under study and conduct excavations with the intention of testing these hypotheses against fresh evidence. And to be fair, this is largely what most archaeologists do today. They just don't realise it. You don't go into a featureless field to dig a hole without thinking, I wonder what could be there. If it's X, why is it there? If it's Y, why is it there? And then you have the post-processual archaeology, and this movement originated in the United Kingdom during the late 1970s and early 1980s, pioneered by archaeologists such as Ian Hodder, Daniel Miller, Chris Tilley, and Peter Ucco, who were influenced by French Marxist anthropology, postmodernism, and similar trends in socio-cultural anthropology, and thus truly scientific archaeological work is difficult or impossible. So this is a sort of juxtaposition to this lot. This is especially true in archaeology where experiments, excavations, cannot possibly be repeatable by others as the scientific method dictates. Exponents of this relativistic method, called post-processual archaeology, analysed not only the material remains they excavated, but also themselves, their attitudes and opinions. And there are people that continue to do this today, particularly on prehistoric sites, I have to say. Some of these complex prehistoric sites, you actually have a mixture of these two archaeology methods of trying to work out what you imagined the culture that was depositing these finds was doing, and how they respected things and how they interreacted with each other, and therefore how you as an archaeologist should interact with that site. Complicated, isn't it? So, bearing all that in mind, or forgetting about it fairly quickly, whichever is easier for you, we have archaeological science proper. And archaeological science started being this, excavation. This was the scientific experiment. What is under the ground? Is it X or Y? And how old is it? So here you see a group of happy archaeologists trying not to mattock each other to death down a hole. And just to make it even more scary, here you have a group of resting archaeologists down an incredibly deep trench in Maiden Castle in 1920. Health and safety was somewhat lax in those days. I mean, can you imagine if one of these poor guys fell down there? How the devil would you get him out? But this was how they used to do it. You know, if you have a large hill fort like Maiden Castle, the largest hill fort in Britain, Credon Hill is only slightly smaller. You wanted to find out what these ditches, the shape of these ditches, what was in the bottom of the ditches and how it differed all the way up. So you got a gang of effectively navvies to dig a big hole for you and hopefully not injure themselves or worse. So, and of course in doing so they remove a vast amount of archaeology. So archaeology is or excavation is a destructive process. And needless to say, we seldom see anything on this scale today, because we now have methods for gaining almost as much, if not more, information from a relatively small series of holes than taking out massive ditch sections like this for, you know, perhaps hundreds of feet along. So modern excavations are usually far less dramatic in appearance, hopefully, smaller in scale and carefully targeted in order to gain the most information out of the smallest intervention. And this really is made possible by the help of a series of what we call the archaeological toolkit for, first of all, finding sites, locating them in the landscape, and then by sort of targeting them and looking at them in a number of different ways. So, it all started in 1906 with Second Lieutenant Philip Henry Sharp, who photographed Stonehenge from a Royal Engineers balloon. The results proved how useful low-level aerial photography is for understanding features and structures on the ground. And basically what he did was he took a series of photographs at different angles, which not only showed the stones sticking out the ground, but it also showed the shape of the landscape around the stones and how those stones related to it. And this sort of baton was taken up by Osbert Guy Stanhope Crawford, 28th of October 1886 to 28th November 1957. And he was a pioneer in the use of aerial photographs. He was in service in the Royal Flying Corps during World War I. In 1920, he was appointed the first archaeology officer of the Ordnance Survey. Ordnance Survey were groundbreaking as far as their sympathy, their understanding and their respect for archaeological features. A post he held until his retirement in 1946. And since then, aerial survey has continued to be used as a cornerstone of archaeological survey. It is dependent on the weather, of course, and the ground condition, but it is also quite expensive. You've got to have a pilot and an aeroplane full of fuel and a photographer, usually hanging out of one of the windows. They tend to like using high-wing planes so that when you bank, you can see out of the window and the wing isn't in the way. It's a very unnerving thing to do, believe me. I've done it. Being cooped up in a very small Cessna, banking around the Black Mountains, you don't want to have lunch. But basically, what it means when you're up in an aeroplane, if you get the weather right, if you get the conditions right, is that you can pick up buried archaeology from 200 or 300 feet up in the air. And this mainly becomes clear when the fields are under either crop or permanent pasture. And it's all to do with moisture in the ground. A lot of archaeology is to do with moisture in the ground, and a lot of our scientific techniques are to do with moisture in the ground. So when you fly over a nice green field, it should be uniform. Very, very few green fields are uniform in shade. And quite often you start to see stripes, blobs, patterns all over it. Some of them are dark and some of them are light. And the light ones are where there's less moisture and the crop is being stressed and it's losing its nutrients. And more often than not, unless the farmer has had an accident with some of his material that he's putting on the soil, it is because there's something close to the surface that is preventing moisture getting to the roots. And in this one, there's a big stone wall. Yeah, and that stone wall is there. So you get crops not growing as high because they're stressed, and crops losing their colour as well. So you get creamy instead of green white lines coming through. And where you don't have a wall, but you have a ditch, you have a negative feature or a post hole or a pit, that fills with more moisture, and the grass or the crop grows faster, higher, and is darker in colour. And it shows up. So as you fly around, you can see these, you can work out which field it is, and nowadays we can using global positioning systems, and you can take the photograph, match the photograph to the field, digitise it onto a map, and actually draw archaeological sites that on the ground you wouldn't know were there. And it's superb. It really is. That's the Roman town of Kenchester, or Magna Castra, just outside Bishopston by Credon Hill. That's the summer, and this is a pasture field, and there's the main road, the Roman road. You can see, if you're eagle-eyed, there's a black stripe or a green stripe running up it. That's the central drain. You can see the alleyways and the side streets running off it, and you can see the ghost remains of buildings running all over it as well, and that there is the wall of the Roman town running around it. It had a wall running all over it. So it's remarkable. That's you know, a good 30-acre field, and you've got the entire skeleton, if you like, of a Roman town, and you can see how much of the Roman town was built. It didn't fill every inch of inside the walls, but you had this main road, you had these little side roads and lanes and alleys, and then you had principal buildings off the main road and some set back as well. So, you know, that gives you far more information than wandering around that field trying to pick up bits of pottery. Yes, we know it's Roman, but being able to see the plan of it is fantastically useful. And of course, our extant monuments show up beautifully if the light is right and you have a good photographer. So this is British camp on the Malverns, and not only can you see the superb ramparts, but you can see all these smaller trenches and bits and pieces, these little terraces running all over it from where they were building huts for when they were living and working up there on a seasonal basis. And it shows the monument in its entirety and relates it to this part of the Malvern Hills, and then Worcestershire on this side and Herefordshire on this side. And, you know, a picture paints 1,000 words. Well, this one particularly does. So, aerial archaeology has identified more archaeological sites than any other method currently available, but it has limitations. And the main limitation is ground cover, trees particularly. You can take photographs of trees all you like, whether it's winter or summer, and you see trees. Fairly recently, we've got around this by LiDAR. Most of you may have heard of LiDAR over the last few years. It's become increasingly useful, particularly for mapping land for areas that may or may not flood. And LiDAR stands for light detection and ranging, and it's a remote sensing method that uses light in the form of a pulse laser to measure ranges, which are the distance from an aeroplane down to the ground, and of course the ground isn't flat, to the Earth. These light pulses, combined with other data recorded by the airborne system, generate precise three-dimensional information about the shape of the Earth and its surface characteristics. So it basically draws the topography, but it goes through vegetation. So it will disregard things like bushes and trees. A LiDAR instrument principally consists of a laser scanner and a specialised global positioning system receiver. Airplanes and helicopters are the most commonly used platforms for acquiring LiDAR data over broad areas. But again, it's very expensive. You can't just say, can you do LiDAR over one of my fields? Because to hire one of these things with all of this kit and to get all the information back is prohibitively expensive. But Natural England, for those of you that are interested, have all the data up to, I think it's 2 meters, and it's free to download. So if you need it, that's where it is. And the results speak for themselves. That is Credden Hill Hill Fort without any trees on it. That's LiDAR. So this is absolutely covered in trees, the whole of Park Wood. And here you can clearly see the ramparts. You can clearly see later quarrying here and up on the top here. You can see the routeways in and the trackways around here that are old. You can see the modern trackways from for the forestry and around here. You can see things like, where is it? This one along here, which is the Deer Park Pale, which comes up round here. And you can see a big sort of square thing in here, which you can't see on the ground, but parts of this at least are based on an enclosure for a Roman fort. And we've tested this by excavation but from 2007, 8 and 9. And for the first 2 years of our excavations up here, we failed to find anything Iron Age in this huge Iron Age hill fort. We were still going through Roman material. And just like Brandon Camp, it appears that they were using a deserted Iron Age hill fort to use as a military base and station for the storage of goods and people whilst they built the infrastructure of the Roman roads and the town of Magnus or Kenchester that we saw a couple of slides ago. And you can also use it in an urban setting. That's the city of Hereford through LiDAR. And what it's done is get rid of most of the buildings, or at least smooth them out. We've messed about with the vertical scale here to try and accentuate things, the topography. So that's Aylstone Hill, or Aylstone Mountain as it looks today. And that is Castle Green with the rampart running round it. The little square bit there's the Bowling Green, and the black thing is the Nelson Monument. But at a glance, it's very useful at showing perhaps why Hereford is where Hereford is. You've got the Ironbrook and the Azer coming through here. Basically everything that's blue is where the water wants to lie. So there's the River Wye coming through. But it also shows how the topography varies and how a lot of Hereford, or the historic core of Hereford, is built actually, this red area, on a spit of gravel that comes through here and round. But it's bisected by this little finger of yellow and blue, which is the King's Ditch, as it was called. And it's basically draining from this big blue blob up here, which is Wide Marsh, the Wide Marsh. And the water drains naturally through here and runs down into the River Wye. The old Wye Bridge is just there. It shows how actually Hereford City, in its sort of late Saxon period, was almost two cities. You had this bit, and this is where the cathedral is, and Cathedral Green, and all the canons' houses, etc. So you had the religious Hereford, and then you had the area that was owned by the king, which is why it's called the King's Ditch, and that was the industrial part of Hereford, which is here. And again, this has been tested by excavation now. But it shows it really nicely, and it's nice, because otherwise your eye gets diverted by, things like the church spires, the cathedral, trees, etc. But if we zoom in even more into some of the areas that are again, to do with the buildings, here you can see just how distinct the King's Ditch is and how far it runs right through. I mean, Broad Street is just here. This runs almost straight up Aubrey Street. When they put in a gas main in the 1960s across here, they found that in the early medieval period, they'd made the road go over this by using tree trunks because they floated and it didn't sink so much. So there's a Cordera road running across here where King Street is now. So it's very, very useful. But if you zoom in even more, particularly in some of the low-lying areas, so this is the Bishop's playing fields. So this is the River Wye. The Bishop's Palace is just over here. That's the leisure centre, believe it or not. But if we forget about these strange pointy things for a moment, what I'll draw your attention to is this, and this is medieval farming, all over King George V playing fields. This is the Roe Ditch coming through here, but even on the other side of Roe Ditch, you've got evidence of land tillage, of what looks to be orchard ridging, whereas out here you can see the gentle curve here. This is proper ridge and furrow ploughing, none of which you can see properly on the ground at all. So from an archaeological point of view, for mapping, this sort of stuff is really, really interesting and really, really good, because of course you can plot it straight away and you can see how well it's preserved or otherwise. So LiDAR is a very, very useful tool. But, as I say, it's expensive. You have to wait for a major agency to want to do in a whole area. So we've started to get round this by the use of our own little aeroplanes called drones, or unmanned aerial vehicles, UAVs. And there are various companies. Aerial Cam was one of the first to get involved with this. In fact, Adam Stanford, who's in charge of Aerial Cam, was a pioneer aerial photographer from the ground. And this thing here is a 30-metre pole that he swings down, and it's hydraulic, and he used to put a camera right on the top and do vertical photographs. But he's now branched out into these wonderful little things, or not so little things, these drones, or octocopter, as this one's called, because you can put quite a large payload under some of them. The trouble with these small drones is that A, the batteries don't last very long, and B, you can't sling a big high quality camera or scanner underneath it. So this thing is Wi-Fi enabled to send data directly to a device in the field, so a laptop. So it captures all the images straight away as a film or as still shots, but it also produces, besides photographs, three-dimensional ground mapping called structure from motion, which is similar to LiDAR, and it's automatically georeferenced. So again, it draws a physical three-dimensional view of the topography on the ground. And instead of being 2 metre or 1 metre or half a metre density as far as LiDAR is concerned, this thing will go down to about 10 centimetres. So you get far more detail, but over much smaller areas. And compared to an aeroplane or a helicopter, these things are much, much cheaper, and the results are just as good. And you can use them in places where larger aircraft can't go. So you can actually now have ones that will go through doorways, and you can zoom them around, say, Hereford Cathedral, and photograph everything on the floor, all the tiles, and map them if you wanted to, or to inspect the trusses in the roof or something like that, which saves a bundle on scaffolding and people wearing harnesses swinging around, and you don't really have to shut the building for more than about half an hour instead of a week. So very, very useful, and this is the sort of thing that he can do with it. This was us in 2016 at a place called Ponthenry Castle, just near Longtown. Ponthenry Castle is under there, or at least the motte for the castle is. That's one of the ramparts. But it's not terribly visible. That's it on the ground. Beautiful, wonderful conical motte with a moat around it. But trying to photograph it is very difficult. But if you use Adam's camera, it takes away all the vegetation. So you can suddenly see just how circular this is. And this model you can spin around to any angle you want. So you can show the detail and the relief by spinning it around to show and accentuate the rampart, etc. And again, if you look quite closely, you start to see that there's a series of lines running through here and this down the middle. And this, again, was actually used as a garden in the 18th and 19th centuries. And this is orchard ridging, again, and drainage for a vegetable plot that was down there. This castle we excavated in 2016 and 2017. We put trenches through here and in here to look for buildings, and on here to see if there was a tower and if it was made of wood or stone. And the remarkable thing about this castle is that it was a castle that was built like this, an earthwork, but never used. And this is fascinating in as much as Herefordshire's got a lot of castles, as has Shropshire and Monmouthshire, and a lot of them are motte and baileys, very simple things like this. And for many, many years, people have sort of wondered how they actually manned and used these castles. And it appears that certainly the Norman invasion was done so fast that there must have been a sort of battalion of almost sort of Royal Engineer castle builders, if you like, following up or even perhaps going ahead of the main military force, creating a simple motte and bailey and then moving on to the next one. And some of these were used and some of them weren't, because the sort of the military might and the political will moved so fast up some of these valleys. So by the time Pont Hendry was built as this earthwork castle, everyone had moved off up further towards Llanfano and discovered that there was an old Roman fort at what is now Longtown, which they plonked one of these on the inside, and that became the castle. But this was never used during the medieval period for anything. And believe me, my volunteers got very bored after 2 years digging holes in that and finding absolutely nothing, which I would never have believed. So LiDAR and structure from motion and drones in particular have been very useful for me over the last 5 or 6 years. This is a series of fields just north of Leominster at a place called Morton, or just south of Alderton, which some of you may have heard about. It's been in the newspapers a little bit over the years. And I was tasked back in 2015 to try and find the exact location of where a hoard of coins and treasure was found that was then stolen from our county. I used whatever scientific methods I could to try and find out what the topography was like and where there might have been an archaeological site which could have contained a Viking hoard or something similar, not knowing anything about where it came from except which fields vaguely these people had been in. So I had 54 acres to play with to try and find a spot or spots where this stuff came from. So we had the drone go up, and this of course photographed the site as it was back in late 2015, early 2016, but as it was doing it, it also recorded it through its underlying topography without the crops and without the trees. So, for example, that little finger of land up here is that wood there, and that lump in there is a big quarry, and the track goes up the middle of it. This lump in here is this wood here, and you can see the planting lines through it and a quarry, and this little lump in here is this little lump here, and that's another quarry. But under all that, you can actually see the lines from medieval ploughing coming through here and across there in what is now woodland, and also a lot of it round here, medieval ploughing going this way, and some of the old field boundaries as well. So from that point of view, it's quite useful. It strips away everything that the eye wants to see and wants to concentrate on. But the other thing that it does is it takes exact vertical images of an area, and because it's such a sensitive and high definition camera, it lets you zoom in a long way. So these fields here are covered in maize. This is the maize, and I was tasked with trying to find areas of disturbance within that maize. Now, on the ground, this stuff is taller than me. And as you can imagine, the landowner wasn't terribly keen on having a bunch of beardy archaeologists wandering through his maize crop, just 3 weeks before it was due to be harvested and flattening most of it. So we used the drone to take these photographs and then zoom in and map through the GIS data and GPS data where there were gaps in the rows where people may have disturbed the seed when they were digging the treasure up or whatever, when they were metal detecting back in June of the year before. So we mapped things like that where there was 1, 2, 3, 4 plants missing because somebody could have dug that hole there and the plants may have been disturbed and died. But we were also able to differentiate between areas like that, which have bare earth, and areas like this, which you can see the crop's been flattened underneath, and that's badgers messing about in here. So we could discount areas like this, but record areas like this. So that was quite useful, and that's without walking anywhere. So, I mean, this is a screenshot from another lecture. As you can see, I'm slightly biased, modern day pillaging. But it's a fascinating story. And not only, of course, the scientific method of metal detecting, whereby we did our own metal detecting to make sure that the fields that we were metal detecting had already been metal detected. It's quite easy to find out which ones have been metal detected because all you find in these fields normally is iron and lead. Metal detectors now, you can switch off signals from base metals, let's say, because they're so distracting and you find so many bits of tractor in these fields. So you can set them to find just non-ferrous metal, for example, or stuff with nickel or gold or silver in. So we had a team of metal detectorists who went through 54 acres, re-metal detecting, picking up every metal thing that they found, which was quite a lot of bits of tractor, and bits of lead, and mastitis tubes. And if you've been in the game for as long as I have, if you start to find mastitis tubes lying in sort of stripes, it's where they've been dug up and then thrown into the hedge so you don't dig them up again if you're a metal detectorist. So we use this, and this is just a selection of bits and pieces that they found, which we've recovered. These are now in the British Museum. They will come to Hereford when we have sorted out the provenance, the legal owner, and the value of them. But they are fantastic things. And a group of coins and various other bits and pieces as well. But we also did geophysical survey. So the other thing that we did was look at the photographs from the two metal detectorists' phones. And here's a word of warning. Don't take a photograph of anything you don't want anybody else to see on your phone. These photographs have been deleted and they're still here. You can get photographs back on a mobile phone very, very easily. I know far too much about these two guys now, which I didn't want to know in the first place. But out of the X thousand photographs that I had to sit in Hereford Police Station and look through on a PowerPoint presentation like this, I managed to identify a series of photographs of the pieces of treasure that were found, and the coins in the ground, and the artifacts in the ground, and then the whole group of artifacts laid out tastefully on a Tesco carrier bag. So, you know, technology can be useful, but it can be dreadful as well. And amongst these photographs were two clinchers, this photograph and this photograph. This is the same field, and you can see when they were there before the maize grew up. And I recreated those photographs. I took these with me and stood in the same field and took a photograph that way, so you can see that tree, and all this are the same. And then the same this way. These trees here are very distinctive, and they actually join up. So this corner joins onto this corner, and so forth. And they've taken a photograph, and it's the only landscape photograph of the entire area of the corner of this field. So we went back and undertook intensive geophysics, and there are two main types of geophysics. One deals with water and one deals with magnetism. The first one is the water one, resistivity. It used to be called an earth resistance meter back in the day before it had data loggers and all these sorts of things on. And it was literally just a needle on a dial, which went to a number eventually when it settled down. And you wrote it down on a square and entered it into the BBC microcomputer of the day. Seriously. That's back in the 1980s. But basically it's a series of metal probes with electrodes that are inserted into the ground to obtain a reading of the local electrical resistance. So it passes a current between two probes. And if there's a lot of moisture in the ground, of course, the current gets from this probe to this probe very quickly. So you get low resistance. And if it's stony and dry, you get higher resistance. And it maps it. So a variety of probe configurations are used, most having 4 probes, 2 mounted on a rigid frame, and 2 probes put down in a controlled area that don't move. And you measure the difference between those two, and compare it. So they're the voltage probes, and they're used to measure the voltage, which indicates the local resistance. In general, greater probe spacings yield greater depth of investigation. This will go down probably about 1 metre, depending on the size of the archaeology underneath. And this is a sort of plot that you can get. So this is picking up stone walls. So if this was in pasture and it was a drought year, that would show up as dark green and this would show up as much lighter green. But in the absence of having the good weather and an aeroplane or a drone, this will pick it up in most weathers, because no matter how wet it gets, there's always going to be a difference between the amount of water in a stone wall and the amount of water in wet earth. And again, it gives you a very good and accurate plot of what is under the ground. And this is what we used for our trying to work out where they were digging holes. So we did resistivity all through here, and then on the basis of what was found here, the anomalies, basically we were after negative features, small pits, about 1 metre in diameter or smaller. We then did a series of hand-dug trenches all over the place to see if we could find anything left that the detectorists had dug up, or if these pits were anything else, like natural or tree throws, or to do with the farming techniques that have been used here. So it narrows it down rather than trying to search 54 acres. Magnetometry is basically a survey using a sensor which measures the magnetic field strength. So basically all it does is it looks at the earth and picks up different magnetisms. So you can arrange these depending on the depth and the type of soil that you're using into different configurations. And every kind of material has its unique magnetic properties, even those that we don't think of being magnetic. And minute magnetism works as well. So different materials below the ground could cause local disturbances in the Earth's magnetic field that are detectable with sensitive magnetometers. And here you have a plot here. This is a concentric ditched enclosure. And what has happened is that the minute chemicals and trace elements in the ground have reacted differently where they're wetter and give off a different type of magnetism. And this picks up that and again plots it for you as you walk along. So if resistivity is not possible, and if this is deep or much smaller in scale, then it may be more apt to use this sort of thing. So the only problem is if you have anything big and magnetic. So you can't use one of these within 10 feet of a barbed wire fence, because the barbed wire would pick up on this rather than anything else, and it would go off the scale. Or in the case of one of our sites, if there's a gas pipeline like that one, the red and blue is basically it saying it can't cope, it's gone nuts. But the rest of the field here that we've done it over shows up quite well, and again, just like the LiDAR, it even picks up the medieval ridge and furrow coming through here, because of the difference in magnetism from the top of the ridge to the bottom of the ridge. And this is one of these kits being used. Because it's such a large area, they actually have one that's towed gently with a quad bike on a sledge, rather than having some poor individual walk up every 2 metres and back every 2 metres up 54 acres. But it's a very good series of methods. And then you have method number 3, which is ground penetrating radar. And this uses pulses of radar, a bit like pulses of laser from the LiDAR method, to image the subsurface. This non-destructive method uses electromagnetic radiation in the microwave band, UHF, VHF frequencies of the radio spectrum, and detects the reflected signals from subsurface structures. So it's a bit like a submarine. It pings down here, hits something, and it gets a signal back. And the problem with this is that it gives you a slice through the ground that, unless you've been doing it a long time, doesn't mean much to the uninitiated, I think it's fair to say. It's a group of sort of waves, isn't it, really? GPR can have applications in a variety of media, including rock, soil, ice, freshwater, pavements and structures. So it's basically used where you may not necessarily be able to use any of the other types of geophysics. And in the right conditions, practitioners can use GPR to detect subsurface objects, changes in material properties, voids and cracks. And like everything else, this is what all these things were designed for. They weren't designed for archaeologists to play with and use. They were designed for engineering purposes more than anything else. GPR uses high frequency, usually polarized radio waves. A GPR transmitter emits electromagnetic energy into the ground when the energy encounters a buried object or a boundary between materials having different dielectric constants. It may be reflected or refracted or scattered back to the surface, and a receiving antenna can then record the variations in the return signal. Now, the hugely good thing about this is that you can use the data at whatever depth you want. So this here is in centimetres, so that's 50 centimetres, that's 100 centimetres. So whatever it is, this is a pit in a house floor, prehistoric house, is, you can tell, is at about 70 centimetres. Yeah? So you now know how far down you have to dig without digging a hole, if you wanted to know, which can be very useful as far as if you're working in the contract field and someone asks you, well, how long is it going to take and how deep is everything, you can then tell them. But the other really good thing is that you can sort of flip the data and turn it into a plan and do time slices, as we call it, through the earth. So here we have the remains of a round barrow. And what we've done here is we've sliced through every 25 centimetres to show how the structure is constructed. So we start off at the very top, and as we go in, you can start to see how it's been built with pits and stones around it, and then the stones start to run out, and then you've just got an earth mound through it, and then the ghost of the earth mound underneath it. So it's very, very useful from that point of view. And that's the sort of thing that we'd be looking at. It tells you where it is, how it's made, and it gives you an insight into the sorts of archaeology that you might or might not be dealing with, which, if you hark back to our archaeological theory element of this lecture, that means that you then can start thinking about what this feature that you think you know about is and how you're going to deal with it in the best ways possible. But the one overriding thing to remember is that despite having access to all these tools, we still need to excavate in order to confirm the nature and period of the site. And this is done by the retrieval of artifacts and samples using set rules and processes. And this is us. This is Manchester and Cardiff training excavation in the Olcan Valley near Llanfeino back in 2010, excavating a Bronze Age cairn, which is one of the nicest cairns that I've ever seen. It's got this curb around it, and it has a series of interrupted curbs with pits with cremations in, and a series of pits and a central chamber with a cremation urn in the centre. Absolutely beautiful. And this is taken from a vertical pole before a drone, and because it's a training excavation, we get the students to do it old school. So they have to draw every stone on a board with gridded paper, just to show them how difficult it used to be when I was their age, although here's me still doing it. So once we've discovered our material, we need to date it. This little cartoon basically says, you're doing cave drawings with carbon sticks, ? And the other guy's saying 1,000 years from now, archaeologists are going to go ape trying to date these because they'll be dating the carbon, not what he's drawn. So there are three main ways of doing scientific dating besides dendrochronology, but the actual science of this is carbon-14 dating, thermoluminescence dating, and something called optically stimulated luminescence. And to be honest, as an archaeologist rather than as a building surveyor, certainly these two, and increasingly this one, is what we use most of the time. So carbon-14 dating, I apologise for all the words, but radiocarbon dating, also referred to carbon dating or carbon-14 dating, is a method of determining the age of an object containing organic material by using the properties of radiocarbon, carbon-14, a radioactive isotope of carbon. The method was invented by Willard Libby in the late 1940s, and it soon became a standard tool for archaeologists. And Libby received a Nobel Prize for his work in 1960. It's based on the fact that radiocarbon is constantly being created in the atmosphere by the interaction of cosmic rays with atmospheric nitrogen. The resulting radiocarbon combines with atmospheric oxygen to form radioactive carbon dioxide, which is incorporated into plants by photosynthesis. Animals then acquire carbon-14 by eating the plants. When the animal or plant dies, it stops exchanging carbon with its environment, and from that point onwards, the amount of carbon-14 it contains begins to reduce as the carbon-14 undergoes radioactive decay. Measuring the amount of carbon-14 in a sample from a dead plant or animal, such as a piece of wood or a fragment of bone, provides information that can be used to calculate when the animal or plant died. The older the sample is, the less carbon-14 there is to be detected, and because the half-life of carbon-14, the period in time after which half of a given sample will have decayed, is about 5,730 years, the oldest dates that can be reliably measured by radiocarbon dating are around 50,000 years ago. So it's complex, but it's very useful. Thermoluminescence dating, on the other hand, is a method of dating archaeological specimens, chiefly pottery, by measuring the radiation given off by ceramic materials as they were heated. So when your pot is fired, it traps the radiation from that firing. So the amount of luminescence is proportional to the original dose of radiation received. In thermoluminescence dating, this can be used to date buried objects that have been heated in the past, since the ionizing dose received from the radioactive elements in the soil or from cosmic rays is proportional to age. This phenomenon has been applied to the thermoluminescent dosimeter, a device to measure the radiation dose received by a chip of suitable material that is carried by a person or placed with an object. Heat empties or resets the thermoluminescent signature of the material. Subsequent recharging of this material from ambient radiation can then be empirically dated by the equation age equals subsequently accumulated dose of ambient radiation to dose accumulated per year. But the good thing is we have computers to work all this out for us now. It's not as bad as it sounds. And then, don't worry, it gets easier after this. Optically stimulated luminescence. The method makes use of electrons trapped between the valence and conducted bands in the crystalline structure of certain types of matter, such as quartz, feldspar, and aluminium oxide, all of which are regularly used in pottery. The trapping sites are imperfections in the lattice, impurities or defects. The ionizing radiation produces electron-hole pairs. Electrons are in the conducted band and holes in the valence band. The electrons which have been excited to the conduction band, i.e. heated, may have become entrapped in the electron or hole traps. And under stimulation of light, the electrons may free themselves from the trap and get into the conduction band. From the conduction band, they may recombine with holes trapped in hole traps. If the centre of the hole is a luminescent centre, radiative combination center, emission of light will occur, and the photons are detected using a photomultiplier tube. The signal from the tube is then used to calculate the dose that the material had absorbed, and the age is calculated by the absorption of radiation dose against the radiation dose rate. So it's very, very similar in many respects. You're just measuring something different. And the radiation dose rate is calculated from measurements of the radioactive elements with the sample and its surroundings and the radiation dose rate from cosmic rays. So you have to take not only the thing that you found that you want dated, but you have to then take a series of samples from the soil and the rock around it to compare and contrast. And that means that you can then work out the date of the thing, or the dose rate that that thing has. The total absorbed radiation dose is determined by exciting specific minerals, usually quartz and feldspar, exciting, extracted from the sample with light and measuring the amount of light emitted as a result. A sample in which the mineral grains have all been exposed to sufficient daylight, seconds for quartz, hundreds of seconds for feldspar, can be said to be of zero age. When excited, it will not emit any such photons. The older the sample is, the more light it emits, up to a saturation limit. So the older, the brighter, for a change. But, and there's always a but, all of these techniques are expensive to undertake. Carbon-14, for example, is about £500 a pop nowadays. So it's got a lot cheaper, but you don't want to waste £500 on a sample that you're not sure about where it comes from, or a question that you want answered. So they're expensive. They're not very accurate, but it gives you an idea. So if you just want one date, if you've got a site, and let's say, for example, that it's got some material in it that you have no idea how old it is, or at least you think it's prehistoric, but prehistoric covers a huge span, then you could send off a piece of charcoal or get a piece of pottery dated or a piece of bone dated, and it would give you roughly, give or take in this one, for example, this is 3,400 years BP plus or minus 130, or 1,400 BC, give or take 130 years in English. So if, therefore, you know that that comes from a Bronze Age site, and it's not Neolithic, it's not Mesolithic, and it's not Iron Age. And for most archaeologists, that's the sort of thing that we need to know straight away for writing a report and working out what specialist is going to look at what material. But if we want to find out how long a site was used for, we need more dates and more accurate dates, because plus or minus 130 years, if a site is only used for 50, isn't terribly useful. And we've got a method now that will do that for us, called Bayesian analysis. Bayesian statistics provide a way of combining different types of information about chronology to calculate explicit statistical estimates for the dates of past events. Statistics are given a series of tests according to Bayes' law, which define and redefine trends in variance and probability. This method has proved particularly effective for the analysis of the complex probability distributions of calibrated radiocarbon dates. And this enables archaeologists not only to date a site, but be able to say, brackets, with a reasonable degree of certainty, that the site was being used for X numbers of years. And this can help when sites have been reused. And there's a couple of examples here. One, again, cast your minds back to 2007, the Rotherwas ribbon. And the Rotherwas ribbon is basically an old stream bed, but it's been used by prehistoric peoples. And what they've done, this had obviously dried up, but they used it as some sort of, this is where I don't like prehistory because I have to use the word ritual things. Ritual just means we don't know what they're doing, okay? But this has been used for ritual purposes as some sort of processual route, and the gravel isn't the bottom of the old stream. This is material, burnt stone, which has been put in with quartz pebbles and pieces of flint. And people have walked up and down here or walked along the sides of here, and as they've been doing that, they've been doing other ritual things like digging pits and putting nice things in them. But you have a surface here, and then you have a surface underneath, which appears to be nothing to do with that surface. And we wanted to know how old that surface was and how old that surface was. So this is what it all sort of meant. It's cut by a Roman ditch, so we know it's post-Roman or pre-Roman. You've got the edge of the natural hollow, but then you've got this line through here as well, and an earlier ditch underneath that line, and then the gravel layers beneath that. So we took a series of samples from the gravel and the burnt stone and bits of bone that we found in there, all of these samples, and the date range really didn't help us. So this is the probability distribution of dates from the excavation, and basically the big square brackets have been used to try and tie them together. But as you can see, the date range can be quite long. The highest probability is that it's here, but the date actually starts back here at sort of just before 4000 BC. But these keep going. So it's not terribly helpful. But because we did a lot of these and then passed them through this statistical model, what we found out was that it narrows it down from this big square bracket here, which basically says it's been used for 2,500 years, to this one here and this one here, which shows that the lower surface was constructed about 2275 to 2050 BC with a 95% probability. So there's that, and the upper lineal surface was constructed at around 1400 to 1000 BC. So we now know that this one is late Neolithic and this one is mid-Bronze Age. And we know roughly how long they were used for. This one not terribly long, this one not terribly long either. But it's interesting that there was a big gap in between and they came back and reused the same monument. So that's the sort of thing that we can use the statistics for and refining the date range. And it's also very useful for checking our sample methods. This is down in the Wye Gorge. This is Simmons Yat. And this was one of my little adventures a few years ago. Somebody found some finger bones sticking out of a tree throw and got terribly excited. And I went to see whether we needed to get police involved and things. It's underneath Merlin's Cave, which is up here. The river is about 200 feet below us on this very, very steep slope. And basically, this chap's toes were sticking out the side of the hill, having a tree thrown out here. So we excavated, this is a pile of stuff that was excavated out of the cave in the 1920s. And underneath this, there's a layer of stone, and you can clearly see somebody lying down, relaxing underneath, behind the ranging pole. So we have a burial. And when we tied him up, and it was a him, we found that he's very, very complete and actually remarkably well preserved. But there are things that certainly shouldn't belong with a normal human being. This bone here, for example, is the broken end of a femur from an ox or a cow there. And there are 3 other big bits of rib that actually fit together that have been laid across his chest. Very unusual, ritual, some might say. I would try and find other words for it. But anyway, somebody thought that for whatever reason they'd either play a trick on us or leave something for this individual after he died. We wanted to find out how old he was. In fact, we found 2 skeletons there and sent off a couple of bones from each for carbon dating. And the dates came back. The 2 individuals, the dates came back very, very close together indeed. In fact, they probably knew each other and died within 15 or 20 years of each other. But the cow bone that we found next to that chap's mouth came back here. So both the burials are early Saxon, about 550 to 650 AD, perhaps around about 630. and are statistically indistinguishable, i.e. they are so close you can't tell. But the date of the butchered cattle bone yielded a Bronze Age date of 920 to 800 BC. So what they've done is they've buried one of the individuals with material from the cave. And they've removed the material from the cave, which we know is Neolithic and Bronze Age in the main, and they've buried him with that. And that's really, really handy to know. It's something that you wouldn't normally know unless you'd bothered to take a sample of that bone as well as that bone to come out with. So that means that not only have we identified the period in time that they were burying people up here, but what these people were perhaps meaning to the community that were doing it. And this leads us back to our archaeological theory of what sort of culture was being organised in this time period in 550 to 650 AD, so after the Romans but before the Norman invasion. And why were they, don't forget the Romans had started at least in some ways to Christianise us by then, but here, clearly this lot were trying something old or different and were actually burying people with grave goods from their ancestors. And that starts you thinking. And there he is in all his glory. He didn't cut himself in shaving, it's just the way I stick them together because it doesn't leave any trace, so you can recarbon date it. But what you have to remember is that no matter what science you use, we never have all the answers, because we will never know why this chappie or why his friend or both of them were buried on that slope below that cave. We will never actually know. We can write a lot about it, but we will never actually know what he meant to the local community, and we will never actually know why he was so interested, or people thought he was so interested in being buried with material that was from a cave that was effectively 1,000 years older than him, or more than 1,000 years older than him. What we do know about him, because we've had nearly everything that we can tested on him, is that he was very, very old, in that he was what is very, very old in those days. Anything over 40 is old in those days. He was in his 60s when he died. He had terrible osteoporosis. As you can see, he had some dental problems, to put it nicely. He probably died of a cyst in his mouth and blood poisoning, they think. And he spent a lot of time sitting in musty air in something like a damp cave. And they can tell this from the remains of his nasal cavity. So the suggestion and the way that archaeologists think about this, backed up to a degree with science, is that this old chap, and the other one was the same sort of age when he died as well, and had broken his back, but it had been reset and he'd been looked after. He obviously couldn't work, so people were feeding them. These two people were effectively hermits living in and around the cave, and one assumes they were looking after the contents of that cave and effectively providing a link back to the people that lived there 1,500 years before the people that now live there in his age. And all of that is from those 3 carbon-14 dates and the scientific methods we used to look at the bones, which is a huge amount of information. And if I was so inclined, it could provide me with many, many years of writing, guessing what these people were doing, and then other people guessing different things, of course. And let's face it, if you don't know how a culture is run, and a lot of prehistoric archaeologists at least write book upon book about what's happening in Avebury or Stonehenge, etc. But the true answer at the moment is, and I think this is a nice thing, don't get me wrong, it can be frustrating, is that we'll never actually know what these people were actually doing and when and why. But that's archaeology. And in a way, I hope it doesn't change. And the main thing that I hope doesn't change is that we will need to dig a hole. Even if it's only a very small hole, because digging the hole is the fun bit. The rest's very clever, but you don't need an archaeologist necessarily to do the rest. What you need to do is have an archaeologist to contextualize, if you like, this to the site and try and make that link. So with that, any questions?
Well, thank you very much.
Thank you.